All right, let's jump right into it. Welcome to this explainer. Look, if you're a Web3 security researcher, a smart contract engineer, or an infrastructure architect, you already know the deal. Moving value across different blockchains is easily one of the hardest problems in our entire industry. So today, we're doing a highly technical deep dive into cross-chain security architectures. We're going to deconstruct the current landscape, figure out exactly why legacy bridges had such catastrophic vulnerabilities, and then take a really close look at the architecture of modern interoperability protocols. To really grasp why this matters so much, we have to talk about the collateral damage. $2.87 billion. That is the staggering amount of capital that has literally just vanished into thin air due to cross-chain bridge exploits. We're talking about nearly 40% of all value stolen in Web3 being drained right through vulnerabilities in cross-chain infrastructure. So, yeah, the financial stakes here are absolutely massive. Okay, let's dive into this because this specific statistic from the research is just chilling. A 1 in 150 chance that any given bridge dollar will be lost to an exploit. I mean, in traditional finance, those are essentially the odds of playing Russian roulette with institutional capital. There's just no way around it. For an industry trying to onboard traditional finance and heavy institutional capital, those odds are completely unacceptable. This isn't just some random bug in a single smart contract. It's a systemic architectural problem spread across the entire ecosystem. So, here's our roadmap for today's explainer. We'll start with the cross-chain security crisis, then trace the evolution of bridging architectures, dive deep into CCIP's architecture, compare protocol performance and security, and wrap up with the future of tokenized assets. Section 1, the cross-chain security crisis and those multi-billion-dollar hacks. So, the bottom line is that cross-chain protocols are inherently incredibly complex. You're dealing with heterogeneous chains, completely diverse consensus mechanisms, and entirely different coding languages all interacting at once. Engineers have to somehow master distributed systems, applied cryptography, and smart contract security simultaneously. But you know what the biggest vulnerability highlighted in the research actually is? It's what's called decentralization theater. A protocol might brag about having decentralized verification, but if the observation layer underneath it all is centralized or opaque, you basically have a single point of failure. If bad data enters the system because an observer gets compromised, well, it just gets verified anyway. Garbage data in, garbage execution out. Throw in some insecure private key management and faulty code, and you've got a perfect recipe for a billion-dollar drain. Moving right along to Section 2, the evolution of bridging architectures from legacy to next-gen. The industry has basically been forced to adapt, shifting from first-generation legacy models to second-generation infrastructure. Now, those first-generation models were your classic lock and mint bridges. You lock an asset on chain A, you mint a wrapped asset on chain B. Pretty straightforward, right? But these became massive honeypots, super prone to exactly the kinds of exploits we just talked about. Because of that, the industry has aggressively shifted towards second-generation messaging protocols. And the key difference is these aren't just for transferring tokens anymore. They're generalized infrastructure layers that can actually send arbitrary data and execute programmable token transfers across chains. The sheer scale of this shift is kind of wild to look at. Generalized messaging protocols are laying down the underlying foundation for lending, decentralized governance, yield farming, and NFTs across over 60 different blockchains right now. We've seen over 900% year-over-year growth in transaction counts for these networks. They've essentially become the new communication highways of Web3. Which brings us to Section 3, a deep dive into CCIP's defense in-depth architecture. Now, what's really interesting here is the triple network setup. Unlike legacy systems that rely on a single, monolithic validator set, Chainlink CCIP totally separates its operational duties. You've got the committing decentralized Oracle network, or DAwn, on one side, the executing DAwn on the other, and sitting right in the middle, completely structurally isolated, is the risk management network. Let's define exactly what that risk management network does, because it's a massive differentiator. The RMN is this independent set of nodes run by a totally distinct set of key holders. But more importantly, it runs a completely different code base, written in a different programming language. It's designed that way for client diversity. It basically acts as an independent watchdog, constantly monitoring for anomalies. If something looks sketchy, it has the authority to proactively trigger emergency shutdowns, or essentially curse a contract to halt operations. This strict separation of execution from risk management is what actually creates a true defense in depth, level 5 security standard. Let's actually walk through the life cycle of a cross-chain message to see how this plays out in real time. Step 1. The committing dawn observes the event on the source chain. It reaches off-chain consensus and writes a Merkle route of that state to the destination chain. Then, Step 2. The risk management network independently observes that exact same source chain event, constructs its own Merkle route, and compares it against the one submitted by the committing dawn. Only if those two perfectly match does it bless the transaction. Finally, Step 3. The executing dawn steps in, submits the cryptographic proofs, and finalizes the execution on the destination chain. This cryptographic separation of duties, it's explicitly designed to kill single points of failure. But it doesn't just stop at the node level. The protocol actually bakes in advanced secure by default safeguards. We're talking configurable rate limits that act like circuit breakers during crazy market volatility. You have token developer attestations, which let asset issuers provide secondary proofs before a transfer clears. And for regulated digital assets, there's the Automated Compliance Engine, or ACE, which enforces policy right before the transaction happens. It's all about containing risk at the base protocol level before it ever even has a chance to impact the application layer.
All right, Section 4. Let's impartially compare protocol performance and security.
When we break down the broader interoperability market, we see some really clear architectural trade-offs. Axelar uses a middle chain architecture with its own decentralized validator set, so its primary focus is really broad blockchain compatibility. Layer 0, on the other hand, uses a mix of ultralight nodes and relayers, optimizing heavily for speed and transfer efficiency through a dual security mechanism. And then Chainlink CCIP, like we just broke down, relies on that triple decentralized Oracle network setup, focusing heavily on defense-in-depth security via its independent RMN. The takeaway here is that there's no single perfect protocol for everything. Your choice as a developer totally depends on whether your specific use case prioritizes raw speed, maximum reach, or ironclad security. Actually, leading institutions are starting to realize that relying on just one single protocol is a massive risk in itself. Take Northern Trust's proof of concept, for example. Instead of hard-coding their tokenized asset platform to a single bridge, they built an abstraction layer using abstract message endpoints. This lets a highly regulated financial institution route messages through Axelar, Layer 0, and CCIP simultaneously, verifying the exact same payload across multiple distinct infrastructures. It's honestly a brilliant way to mitigate vendor lock-in and crush single-provider exploit risks. Let's wrap things up with Section 5, the future of tokenized assets and institutional migration. The reality we are facing right now is pretty blunt. Institutional capital is simply not going to migrate on-chain in any meaningful way unless the underlying interoperability infrastructure meets the highest possible security standards. We are talking about traditional finance here, an industry that processes quadrillions of dollars a year. For those assets to be tokenized and safely moved across distributed ledgers, security just can't be an afterthought. It's not an optional add-on. It is the fundamental, absolute, non-negotiable prerequisite for scaling real-world assets in Web3. Which leaves us with this final thought to really chew on. We've seen the $2.8 billion lost to flawed legacy designs. We've explored the complex architectural trade-offs between speed, broad compatibility, and defense-in-depth security. So as quadrillions in traditional assets prepare to make that jump on-chain, you have to ask yourself with absolute seriousness, is the interoperability infrastructure you're currently building on or investing in truly secure enough to handle it? I really hope this explainer has given you the technical framework to answer that question for yourself. Thanks for joining me on this deep dive. Catch you next time.